3 45-minute lectures plus recitations is sort of at the same time a lot, so I can tell you lots of fun stuff. It is also not so much, so we'll see. I'll try to get you excited about this and give you the tools, and then you need to talk to me and come to the recitation to see some of the details. Okay, so this is a workshop on huge groups. So let me start by introducing our huge group. This is the main player that we will be discussing this week. And for this, I'm going to take S, a surface. That's not a group, but hey, of genus G, at least 2. So here's my surface. Sort of a topologist, so I need to draw this. And now how do I get a huge group out of this? Well, I take the homeomorphisms of the surface. So that's huge. That's our huge group, right? This is not finitely generated. This is infinite dimensional in any reasonable sense. And not only is it huge, but it is also mysterious. So we've heard in the previous talk that for these Artin groups, some of these questions in general are open, like, do I have the Tietze alternative always? Do I have somehow negatively curved structures and things like this? All the same is true here. No one has any idea how to deal with this group. In a sense, it's even worse. Let me highlight the following question corresponding this, which is we don't know of a single torsion-free group that cannot embed. So we just don't have tools. That's sort of the point, right? We have nothing to say about it. Why? Well, really, the mysterious guy, and really the one that we'll be talking about, is not all of the homeomorphisms, but really the mystery comes when you look at the group where all the real topological complexity is, and this is the homeomorphisms that are isotopic to the identity. So these are all homeomorphisms isotopic to the identity. And this is sort of the, I don't know, the evil sibling of the mapping class group. So if you know the mapping class group, this is the quotient of all homeomorphisms by this guy. That's something we like as geometric group theorists. This is where we've gotten rid of all the weird surface dynamics-y stuff, and now we have a finitely generated group that we can deal with. So the mapping class group, which is homeo by homeo 0, is pretty well understood.
If you just did, would it be possible to read what you wrote into?
No. Yes, so we don't know of a single torsion-free group that cannot embed. So the quantifiers are, there's no group for which we can definitely say this cannot embed into a homeomorphism group of this. Right now, I want to sort of contrast this. For mapping class groups, we have a Tietze alternative. Oh, yeah.
Finally generated.
Yes, finally generated. Thank you, Katie. Yes, I meant finally generated. Yes, I need to be careful when there's actual homeomorphism people in the room. Right. So the point is, for mapping class groups, when I take the homeomorphisms mod this strange thing, everything is much nicer. We have a Tietze alternative. We have non-embedding results, like higher rank lattices and Lie groups can go into the mapping class group. We have all these things. And why? Well, a slightly flippant answer to this is, well, this is the finitely generated group, and so we have geometric group theory. Right? So that's sort of the point here. We have lots of very cool tools that don't just come from surface techniques. We also have these. We have topology, but we also have geometric group theory. And geometric group theory, as we all know, is very powerful when you want to prove things like Tietze alternatives or non-embedding things like that. Somehow, the philosophy of what I want to tell you about is that there is a chance of doing geometric group theory even for this enormous group up here. So that's sort of the pitch for what comes in this and the coming 2 lectures. There's a way of trying to push some of the methods from the mapping class group world into the actual homeomorphism world. Okay, so how could we possibly do geometry if I don't have a finitely generated group? Everything becomes a little bit more tricky. But we can do geometry on this group. And there's sort of two ways you can answer this question, and you can see that something interesting can happen here. One is that there's now a pretty well-developed theory of some not finitely generated groups, which nevertheless have a well-defined QI type. This is sort of the work that follows from what Rosendahl is doing. Here, I'm not going to go down this route. Instead, I'm going to tell you that this group carries a natural generating set. And so even though we don't know that this generating set is somehow the universally best way of putting a geometry on it, like, for example, finite ones on finitely generated groups, once you see this, you'll probably be convinced that this is a very natural way of equipping this group with a norm, and then you can try to study it. So how does this work? This relies on something called fragmentation. So this is the fragmentation lemma from geometric topology, and it says what? So in our setting, it says that any homeomorphism F from my surface to itself can be written as a product where each Fi is supported in an embedded closed disk. Yes. Thank you. Otherwise, this is very false. Right. So this is what I was about to say in the next way. If I want to get something that's isotopic to the identity, maybe the easiest way to do this is to put a little disk in my surface and then just smudge around on that disk. Right. The Alexander trick tells us that anything on a disk, any homeo of a disk, is homotopic to the identity rel boundary. So if I put a disk on the surface, then clearly anything I do on there supported in this disk is also homotopic to the identity. And the fragmentation lemma tells us that this actually gets us to every isotopically trivial homeomorphism. And I think the formulation we agreed on is that you will learn more about this in Katie Mann's course. So sort of from the homeomorphism side, why you should believe this to be true. So for us, we'll just take this as a given. This is an input from surface topology, and now this gives me a conjugation invariant fragmentation norm on the group in the usual way, where you just say the fragmentation norm of F is the minimal n such that a decomposition as in the lemma exists. And so in other words, it is the word norm for the generating set, where your generating set is all the stuff that's supported in embedded disk. Okay, so this is nice. Why do I think this is nice? Well, I think this is topologically sort of very natural. These are, in a sense, the simplest isotopically trivial homeomorphisms. They generate the whole group. So you could look at this. Now, this might not be convincing to you. There's better reasons to look at this. One is that it is, in the sense, the universal conjugacy invariant norm on these groups. So it sort of bounds all the other ones. Yes?
I'm used to thinking about compact surfaces, but are you stating the fragmentation limit here for any surface?
So here, everything for me will be a compact. Everything will be compact. So don't worry about that. Okay. Of course, doing geometric group theory on a group is saying more than just saying, well, I put a norm on it and then I'm happy. So this all hinges on the fact, can we say anything interesting about this norm? And then you very quickly realize that it's hard to say anything meaningful about this norm. So here's a basic question. Is this norm unbounded? So that's a very basic question. Don't try to prove this. This is actually kind of hard. So where did this question come from? So this was actually asked by Burago, Ivanov, and Polterovich. Asked this for the smooth version. So this is diff 0 of a surface. And it's also true, though the proof is vastly different, that you can fragment isotopically trivial diffeomorphisms into diffeomorphisms supported on disks. So you have a natural group on the a natural norm on the diffeomorphism group. And Burago, Ivanov, Polterovich asked, well, for a surface, is the smooth one bounded or unbounded? And the reason they were asking this, so why do they care about surfaces, is that in all the cases where we had an answer, so this was in high dimensions or on spheres, the smooth one, they actually knew that this was bounded. So Burago and Polterovich, together with later work of Tsuboy, shows that this is actually bounded whenever I put in, instead of a surface, a manifold of dimension 5 and above or 3, or if I put in any sphere. And so somehow the surface case was just something where these geometric topology tools didn't say anything. So what will we do in this week? We will show the main theorem, and this is joint work with Jonathan Bowden and Richard Webb, that yes, this thing is indeed unbounded. So not yes. Frag is unbounded. And our proof, the one that I'll give, works essentially without modifications, both in the smooth setting and in the non-smooth setting. So this works for homeomorphism, and it also works for diffeom. So how does this work? Why is it so different? Well, we're going to really use surfacey tools. If you know some mapping class group theory, then you'll recognize a lot of things from this proof. And if you don't, you'll quickly see that everything we do is really surfacey. So how does one prove this? Well, this is actually a pretty quick consequence of an algebraic fact about this group. So really, what we prove is that homeo 0 or diffeo 0 admits unbounded quasimorphisms. So what does this have to do with this? So let me very quickly say something about this, and then we'll come back to this in the third lecture. What goes on here is two things. So one thing is that an unbounded quasimorphisms gives us unbounded commutator length. So if I have an unbounded quasimorphism, you don't know what a quasimorphism is, ignore this comment, you'll learn it in lecture 2. But if you do already know, if I have a quasimorphism that is unbounded, you need to have elements where it gets harder and harder to write them as commutators. But on the other hand, things that are supported on disks, you can easily write as commutators. So that's also something you learn in KD's course. And homeos on disk. Right, so that's sort of the first reduction. To answer this question, which is in a sense really about geometric topology, I phrased it as geometric group theory, but really it's geometric topology. To answer this question, what we really do is we try this. We try to prove this algebraic property of unbounded commutator length. And the way we do it is we build quasimorphisms. Okay, how do you build a quasimorphism? I'm sure many of you here will know this, but geometric group theorists have actually become quite kind of good in building quasimorphisms. And what you need for this is an action on a hyperbolic space. So to get the quasimorphisms, we'll build an action of homeo 0 on some Gromov hyperbolic space. Oops. And then we will start to turn the crank on a powerful machine that takes in something like this and spits out a quasimorphism. Now, for the experts and semi-experts in the room, sometimes there's this thing where a little bit of knowledge might be dangerous. So if you think of words like WPD or WWPD in this context, banish them from your mind. This group is more terrible than that. So this is a simple group, which means that you can't possibly get a theory working that's as nice as this. This action that we'll build is very far from cylindrical. It's not WPD, it's not WWPD. It is just barely good enough to get a quasimorphism. If you didn't think these words, wonderful. In lecture 2, you will learn why something like this should make you expect quasimorphism. Okay, but enough setup. I wanted to just set the stage to say what we're up against. So what's our big group? Our huge group is all the isotopically trivial homeomorphisms. What do we want to understand about them? We want to understand that the fragmentation norm is unbounded, which is the classical question from geometric topology. How will we do it? We'll try to cook up an action on a hyperbolic space and use that to build quasimorphisms. Okay, that's the mission statement. So how do we do that? Well, first, how do I get the board to learn? I've been told I should use it in the middle, but that still doesn't help. Okay, so today, for the rest of today, I want to give you a prototype of where this Gromov hyperbolic space will come from. So I'll do something easier. And this is a hyperbolic space for the mapping class group. So I've said in the beginning that that's the one the geometric group theorists really like. That's where I take sort of the opposite. Instead of taking the isotopically trivial ones, I'm taking all homeomorphisms. And maybe now I'm going to do the orientation preserving, but it doesn't really matter. And I quotient out the trivial ones. So at this point, you might say, how could something like this ever help me to study homeo 0? Bear with me for a minute. Well, bear with me for 2 lectures. In lecture 3, we'll push this to homeo 0. And it'll work, I promise you. But for now, all the intuition comes from trying to build an object here where things are much easier. Okay, so how are we going to build this thing? Well, this is a classical object. This is what's called the curve graph. Or the side. Okay, so I can actually write down this space for you very quickly. So what is it? It's a graph. The CFS is a graph. And because it's a graph, to define it, really everything I have to do is I'll have to tell you what the vertices are and what the edges are. And it's called curve graph because it's built out of the curves of the surface. So the curve graph has vertices corresponding to essential. This means that they're not trivial in pi1. Simple. This means that they don't have crossings. Closed curves on S. And we want this group of isotopy classes of homeomorphisms to act. So I better make this up to isotopy. And it has edges corresponding to disjoint representatives. All right, so let me draw a little cartoon. The curve graph is kind of hard to draw, and everyone always draws the same picture, or a quasi-isometric picture, which is deeply misleading, but hey, it's the best we can do. Maybe not the best we can do, but it has to be good enough for our purpose. So this is my surface, and to the right of it, I'm going to draw a tiny, tiny portion of the curve graph. So how does this work? Well, something like this, right? This curve alpha here, this is essential. It can't be homotope to a point. It is simple, it's embedded. So it will define a vertex in my curve graph. So far, so good. Here's beta. Beta is another vertex, and they're clearly disjoint. So there's an edge between the two. Right? That's what we're doing. Let's draw one more. Let's draw this. This is delta. Delta is again clearly disjoint from alpha. And because the algebraic intersection number is plus or minus 1, the isotopy classes of beta and delta really can't have disjoint representatives. So really, there isn't an edge here. So far, this picture is accurate. Let me draw one more. Let me draw this gamma here. This is another vertex. Let me put it here. And now it seems like this guy is starting to intersect things, but really it isn't, right? So these are isotopy classes. So this gamma is really the same as this. I can push this a bit in. So there's these two bigons here. I can isotope these out of the way. So really this delta is joined to all, right? So that's what the curve comes. Seems easy enough. It's not. Maybe if you see this for the first time, the real question you should have is this of any use whatsoever? So we're talking about huge groups. This graph isn't huge, but it's pretty big. So I should say that one thing to immediately observe is that it is locally infinite, right? If I pick my favorite vertex, like beta, and I look at all the vertices that are attached to it in this graph, these are all the essential simple closed curves that are disjoint from this beta. So another way to say this is I cut my surface open at beta, and then I'm looking at all the curves there, and they will be infinitely many. So this is a locally infinite graph. Why is it useful? Well, the mapping class group will clearly act on this gadget as simplicial automorphisms. Right, it'll send isotopy classes of essential curves to isotopy class of essential curves, and it'll preserve disjointness because it acts by homeomorphism. So that's good. And a theorem by Mazur and Minsky tells us that this thing is hyperbolic. So that's the kind of thing we want. We want a hyperbolic space for our group. Let's prove that. We won't give Mazur-Minsky's proof because it's too hard. It involves lots of cool tools. You learn lots of nice things from it, but it's hard. Instead, we will give a very pretty proof by Piotr Pszczycki and Alex Sisto. Piotr and Alex.
It's based on our joint paper with Sebastian and Richard.
Well, yeah. Yeah, well, yeah, okay, fine. I won't complain. So how do we do this? So here's something good to take away. This is sort of a life lesson where life means life as a geometric group theorist. The question is, how do I ever prove that something is hyperbolic? So last time, in the last class, we heard, how do I ever prove that something is cat zero? And we've heard that this is hard, but there's some situations in which there are good tools available. Well, Gromov hyperbolicity is sort of a bit more flexible. This is a coarse notion, and there's a very powerful trick you can use to show that something is hyperbolic. Because the thing is, hyperbolicity means triangles are thin, geodesic triangles. So naively, you might think, I first have to figure out what the geodesics are, and then I can show that they're thin, and this is how I show hyperbolicity. And that's wrong. You don't need to know what the geodesics are, you just need to know something is thin. So here's a theorem we'll use. A theorem. So the one that I'll write on the board is due to Bowden. That's the probably most convenient one, but it has many other versions by many people. So what does this say? So suppose that X is a graph, and we have chosen for any vertices of my graph a subgraph, so that the following holds. Maybe I should pick a number first. So n k is some constant. So suppose I've been able to pick subgraphs with the following properties. Well, the labeling is supposed to tell this, but the vertices x and y are supposed to be in the graph labeled by x and y. The thing is supposed to be connected. So we're on x and y. if the points are really close to each other, then the diameter of this chosen subgraph is at most k. And finally, the triangles formed by these graphs are thin. So the graph between x and y lies in a k neighborhood of the graph between x and z and the graph between z and y. Right, so the picture here is I have x, I have y, and I have z, and I've somehow picked this thing, and I don't quite know how it looks. I picked this thing that connects x to y, and it can be arbitrarily complicated. And I picked this thing that connects y to z, and I picked this other thing. Then, if these look like they have thin triangles, then the graph will be hyperbolic. X is delta of k. So when you see this for the first time, this is in a sense, to me, this was truly remarkable, right? The point is, you don't need to know anything about the shape of these graphs. I'm not claiming that they're efficient. I'm not claiming they're quasi-geodesic. Nothing. They're just some way of getting from x to y, some connected thing. They're not supposed to wander around too much if I try to connect adjacent points, and they have thin triangles. That's good enough to get hyperbolic. And we won't prove this. We will prove a weaker version of this in the recitations, where I'm assuming that these are paths and that they're also compatible undertaking subpaths, which gives you a sort of a hint on why this should be true. But this version allows me to very quickly now prove the theorem. And so this is a good lesson to remember. If you ever want to try to prove that something is hyperbolic, stare at your object and try to guess the geodesics. And you don't have to guess very efficiently. Just guess something that seems geodesic or not. Guess something that has thin triangles and you'll win. Okay, so let's prove this theorem. And so the first thing we do is to replace our graph. As always, there's some sleight of hand here, but this is really sort of a tiny one. So step one is instead work with the augmented curve graph, where we allow up to 2 intersections for an edge. Right? So in the usual curve graph, it's gone now, but in the definition of the curve graph, I put an edge if the curves had at most if the curves were disjoint up to isotopy. Here, I want to join them if after isotopy, there's at most 2 intersections left. And this thing is QI to the normal curve graph. So for hyperbolicity, it doesn't matter which one we use. We'll also do this in the recitations. This is a good exercise to try and play with the definitions of it. Yeah.
Is that going to be true for any?
Yes.
Okay.
Yes. You can pick any number of intersections, and you're going to blow this just up a bit. And now comes the key trick. So suppose that alpha and beta are simple closed curves. Now I need to tell you what a bicorn is. A bicorn is a simple closed curve of the form A union B, where A in alpha and B in beta are arcs. So this definition is a tiny bit too slick for its own good, so I need to say something about this. But I need to say something else as well, or alpha and beta itself. So I want to call alpha a bigon, I want to call beta a bicorn, not a bigon. And I want to call all these things. So why do I think this definition is a little bit too slick for its own good? Because this is the condition on which of these you take. So you need to, in particular, make this so that the boundaries of these 2 arcs are the same, and the interiors of these arcs don't intersect, right? This is part of saying that this union is a simple closed curve. And I want this to be essential, which isn't super essential here, but let's add this to the definition. Right, so let me give you an example of how this would work. Let's draw the typical picture. So what's the point? The point is I can take sort of part of alpha. So this is my arc A, and then alpha somehow continues onward. And alpha continues onward. So this is alpha. And then I take some subarc of beta, which is my B, and beta continues onward, and beta continues onward. And so this thing with two corners, it's called a bicorn. That's where the terminology comes. It also comes from the fact that when you do this with arcs, you have one corner, so we could call them units. Right. So these are the bicorns. And what did I somehow say about this being sort of problematic? Right? Imagine maybe this curve sort of continues onward and intersects alpha like this. So now I couldn't take this as my B and this as my A, right? So then not every way of picking arcs will give me a simple curve. So in taking the bicorns, I'm only taking the ones that actually work. Okay. Now let's go. Let's simply put our gamma alpha beta to be all the bicorns. Or if you really want, it's the full subgraph spanned by these bicorns. So I'm claiming that we can now just apply this theorem and get this to work. Well, let's check. Yes.
What if the bicorn is not essential?
Then we throw it away. But in this case, we want the curves to be in minimal position. So in this case, here, when you're on a closed surface, you don't really have to worry about this, because I'm always going to be assumed that I've chosen isotopic classes which intersect minimally. I should have said this. So in minimal position. And so if you had a bicorn that was inessential, it would give you a bigone, and then you could remove the bigone. So this is important for some. Later we would have to deal with this, but that's why we don't. Okay, so let's go to this wish list here. So we want X and Y to be in there. That's clear by definition. Okay, right. I've added that alpha and beta itself are supposed to be counted as bicorns. Why are they connected? So this comes from the fact that there's a nice partial order on bicorns. So let's say that A union B is less than A prime union B prime. So these are bicorns in this graph. If I'm using more of B. So if B prime is bigger than B. And now you realize that there's always a bigger bicorn. So if I start, the smallest one that I can take is alpha itself. I'm not using anything in beta at all. But if I have any bicorn, I can always take a bigger one. So then there always is a bigger bicorn.
Adjacent to the one you.
Yes. Adjacent to a bigger adjacent bicorn. That's what I'm saying. And so how does this work? Well, let me recycle this picture up here. What you're doing is, so it's slightly different for the very first one. So do that convincing yourself at home or in the lunch break. But let's suppose I have an actual bicorn like this. So what you simply do is you continue following B until you hit A for the first time. And then you see that I can now build a new bicorn where I take this continued path of B and a smaller arc in A to find B prime. and a subarc A prime with the same endpoints. So this is a subarc of A. And now you see that this new bicorn can intersect the old one in at most one point. This depends on if you come back to the opposite side, like I've drawn here, then you do actually pick up an intersection. You could come back to the other side, and then you could homotope it away, and you don't have any intersection at all. Right, so this gives me an A prime union B prime of distance at most one. Right here, we're using the fact that we're in this augmented curve graph where I'm allowing some intersections to connect this. Okay, so this is connected. It is also small if the set I start with is small. And when you keep the criterion on the board. And maybe no one will be surprised by this. Because we all know the really hard work will be to show that these things have thin triangles. So the point is that these have at most distance 1. So this means that the curves intersect in at most 2 points. Then it's easy to see that the bicorns will also all have this property. Right, so all bicorns, right? The bicorns consist of some part of X which doesn't intersect X, and then it consists of some part of Y which can't intersect X in more than 2 points. So this means that they're small. Okay. So now the thing everyone is maybe waiting for, why do they have thin triangles? And this is sort of the magic part of the argument. So what do we need to check? We need to check, I have now 3 curves. So I have 3 curves in the curve graph. You might as well imagine them far away. And I'm going to take, so think of this as alpha and beta. I'm going to take a bicorn between them. So this is here, right? There's somehow this set. And you'll see with this bicorn thing, I'm not really claiming that it's a path. It's just some set. But somewhere here, there's this thing that we want to look at. So this is A union B. So let's draw what we know. Well, this is always the same picture. So let me draw the same picture yet again. So there's A here. And there's B here. This is A and this is B. This is beta. This is alpha. And now, what we're going to draw is I'm going to draw a part of gamma. So if gamma intersects this thing in less than 2 points, then we win anyway. So if the intersection between A union B and gamma is less than 2, then we win, because then this is actually distance 1 from the corner. So otherwise, you have at least 3 intersections. But if you have at least 3 intersections, what does that mean? That means that I can find a subarc. Let's draw it like this. You can find a subarc of gamma, which has both endpoints on, say, beta, and intersects alpha in B and intersects A in a single point. Right? You follow for the shortest amount of time until you hit the same type of interval back. So otherwise, take a subarc C in gamma with the boundary of C in, say, B, interior disjoint from B, and interior hitting A in at most 1, or you flip the roles of B and of A and B. Aha! But now we're done. Why are we done? We're done because now you see that there's this arc C together with a subarc of B, which defines a, in this case, beta gamma bicorn, which intersects the AB curve that we started with in at most 2 points. So we're building here a, in this case, C union B prime, which has actually distance 1, and it'll be on this path here. Running out of space because my criterion is too big, but let's write it here. And a little box because I'm also running out of time, I think. Yes. So this shows that C union B prime, or B prime in B, this is somewhere between beta and gamma, and the distance between this and this. And so you win. You see that these things have thin triangles. So now by the criterion, we know that the curve graphs are hyperbolic. Right, so let me sort of emphasize again how useful this way of proving hyperbolicity is. We didn't have to understand the geometry of these paths. And if you've played around with curve graphs a bit, and I think this is why it took people a while to realize that one could do games like this, doing these surgeries is a very, very inefficient way of moving about the curve graph. It's not like intersection number is a good stand-in for distance. And it's not like, as I sort of do these surgeries, I make progress in the curve graph. These things, they can get stuck for arbitrarily long times and not make any progress at all. So really, what we're saying here is that this thin triangle condition is so strong that you can force hyperbolicity just from knowing something with thin triangle. Okay, there's something I wanted to do today which I didn't get to, so we'll do that next time. And this is, how do we know that this action isn't completely silly? So it could be that this graph has just finite diameter, and well, an action on a point is an action on a hyperbolic space. So just an action on a hyperbolic space clearly isn't good enough. We need to know that this action is somehow interesting. And so we'll talk about this a bit in the recitations, and we'll talk a bit about this in the next lecture as well, to see that this action is really interesting. Okay, thank you.
Are there any similar criteria for spaces that each other are?
I mean, this doesn't really use graph. So the analog of this, if you phrase it correctly, will be true for anything. You want to be able to coarsely go from anywhere to anywhere. I mean, you need some safety assumptions. You need some kind of thing like a geodesic space or something like a length space in a geodesic space. And then if I have graphs that coarsely go from everywhere to everywhere, and you have conditions like this, you should be able to prove a hyperbolicity criterion.
Let's thank Sebastian again.
Yeah, I should say something about the homework. So the homework will talk about adding details to a proof that has to do with flat geometry. And you haven't hallucinated. I haven't gotten to this. So we can either, if you're ambitious, try to do this homework problem from scratch, and then we'll talk about it, or I'll talk about it at the beginning of next class. We'll talk about it tomorrow.